I'm Gokul. Today I'm going to talk about our work on estimating mutual information. So first, I'll give a little roadmap of how I plan to spend the next 15 minutes or so. First, I'll go over the basics. I'll tell you what MI is. I'll explain why we care and why it's hard to estimate. And then I'll talk about our approach, which we call LMI. And then I'll go over some empirical results where we try to understand what regimes LMI can be useful in. And then I'll look at a real problem. So we'll study sulfate decisions in hematopoiesis. And then lastly, I'll just show you how you might be able to use LMI through our Python package. Okay, so first, what is MI? There's a lot of ways of thinking about MI. Today, I think the most useful way of framing it is just a really general measure of statistical dependence. So you can imagine you could have like two variables with a kind of complicated relationship. Maybe it's nonlinear. Certain correlation coefficients might not capture it, right? So Pearson only gets linear ones. Spearman only gets monotonic ones. MI is special in that it can capture any type of relationship. So yeah, I think it's useful to think about it as just a very general measure of statistical dependence. So I'll go over very briefly just a few basic properties of MI. So unlike a correlation coefficient, it's not like -1 to 1. It's bounded below by 0, and that's it. So there's like no negative information is one way of thinking about it. It identifies independence. This is a really important property. So the MI of two variables is 0 if and only if the two variables are statistically independent. And the idea is that the higher the MI is, the higher the dependence is. And then one more property that's really important and really useful is that MI satisfies something we call the data processing inequality. And the idea here is that you can't increase the MI between two variables by transforming one of them. So what I've shown is like not actually the full formal statement, but you can think about it basically as like whatever function f you pick, you cannot make I of fx and y greater than I of x and y, right? Okay, so beyond this, there's a lot of really nice properties when working with MI. So first is that it generalizes not like across continuous and discrete variables and even mixtures of the two. It generalizes to vector, like multivariate random variables. Another really nice property that we won't really get into today is that it can be interpreted in terms of bits. So like the bits on a computer, like for storage. But for today, we won't really talk about that. And lastly, it can decompose into pointwise contributions. So you can imagine that like for two variables, maybe there's like a certain part of sample space that has like dependence enriched there. We can quantify that enrichment of dependence in certain parts of sample space by decomposing MI into its pointwise contributions. Okay? So because of all of these really nice properties, MI is used super widely across like basically every field of science. I picked a few here because they're amenable to nice pictures. I think one application that might be familiar to people in this audience is like for network inference, for like GRNs or signaling networks. You can imagine quantifying the strength of a connection between two nodes as like the MI between those two variables. But one thing you'll notice is that in like basically every application of MI that you see in real world with real data, people mostly only use one-dimensional data. I think a big reason for this is like a technical limitation, which is that it's super hard to estimate MI for multidimensional variables. So a lot of times this is like implicit, right? But it's sometimes written explicitly in papers. So here's one quote from a paper from Alon Klein's lab, which we'll revisit shortly, but it basically says they wanted to estimate MI between single-cell RNA-seq states, but the dimensionality, which is like thousands, is just way too high, so they couldn't actually do it. And instead they resorted to heuristic methods. We'll revisit this one in a little bit. But the reason MI estimation is hard in high dimensions is kind of like the classical reason density estimation is hard in high dimensions. It's like the traditional cursive dimensionality. In practice, what does this mean? So there's like two kinds of popular estimators that people use for MI. There's like an old school, like 2004 non-parametric estimator called KSG, which is really powerful when you have small sample sizes. It works really well, but it kind of breaks down after 10 dimensions. It doesn't work super well after that. More recently, people have developed variational lower bound estimators. Two notable ones are MINE and InfoNCE, sometimes used in contrastive learning. And these can work, they can like scale up better to higher dimensions, but they tend to be super data hungry. So if you're like in a regime where you have say like 100 or 1,000 samples, it doesn't matter what your dimensionality is, you're really going to struggle to get a good estimate out of the variational bound estimators. Okay, so this is kind of the landscape, and the problem we want to solve is basically we want to have a sample-efficient estimator that works well in high dimensions. But at the same time, we can't really beat the curse of dimensionality. It's pretty fundamental. So the approach we're going to take, which we call latent MI approximation, is basically to make just a super strong but potentially reasonable assumption about our data, which can let us estimate MI. So the assumption in particular is that our high-dimensional data has like some meaningful low-dimensional structure. I think this is a really common implicit assumption in basically all deep learning methods, maybe. But OK, so you take your two high-dimensional variables, super hard to estimate MI. What we're going to do is just super simple. We're going to try to learn compressed representations of those two high-dimensional variables to turn our hard problem into an easy problem. And the question is just how do we learn those representations? So one sensible thing to do would be to use like the classical approach of autoencoders to compress our data. So you could imagine if you have two variables x and y, you just have two autoencoders. You learn two compressed representations, then you estimate MI. This seems reasonable, but there are some situations where this won't work very well. So we can look at one example. You could imagine both of your variables have a bunch of independent dimensions, but then they have like one really rare pair of strongly correlated dimensions. If you just have these two independent autoencoders, you have to throw away some information in your representation. Maybe you'll throw away that one strongly correlated component, and you'll end up with this idea that the two variables are independent, when in reality there is some dependence there, it just got lost. So the thing we want to do is we want to try to like take this framework, but we want to like add a regularization, which allows us to like preferentially retain the mutually informative structure in our data. So there's a number of ways you could do this. One really simple way is to just try to predict one variable from the latent representation of the other. So predict y from like zx, if you will, and x from zy. So this is a super simple approach where now you just have 4 decoders instead of 2, but same setup. I think intuitively it might make sense that this will retain mutually informative structure, but we can show this mathematically as well. Optimizing this with like MSE error on the 2 decoders is going to be equivalent to minimizing an upper bound on the difference between the latent MI and the true MI. Okay, so I won't go over the details of how that's done, but you can look in our paper. It's quite simple actually. Okay, so what's the workflow now? So what we do is we take half the data available to us, and we use that data to train or to learn those compressed representations with mutually informative structure. And then we're going to take the other half of our data, put it through the encoders, and then use our favorite non-parametric estimator, KSG, to estimate the MI. OK, so in what regime is this useful? The way we answer this, to begin with, is to look at synthetic Gaussian data, because it has analytically tractable ground truth. So what we do is we just sample multivariate Gaussians, and we control the covariance structure of the Gaussians such that there is a low-dimensional dependent structure between our two high-dimensional variables. So we have like an ambient dimensionality we can call D, which is like the actual like real dimension of the vectors. But then we have some lower number K, which is the intrinsic dimensionality of our dependent structure. And we can change D and K and see how well our estimator works for different K and D. And we can compare this to three popular estimators. So what we do is we study specifically this like low intrinsic dimension, high ambient dimension regime. So we go up to K equals 9 and up to D equals 5,000. And kind of arbitrarily, we choose 2,000 samples for each problem. So we think this is like pretty sparse, especially in this dimensionality. And we use LMI with 8 latent dimensions. So most of the time in this benchmark, we'll have more latent dimensions than the intrinsic dimensionality of the data. But sometimes, for the last case of K equals 9, we'll have a latent representation which cannot possibly capture the truth structure. OK, so if we do this, the 3 like popular methods, info, NCE, KSG, and mine, do really well at the top when we're in the tens of dimensions. But then they kind of fall apart as you go further down, especially to the hundreds or thousands. LMI, however, stays consistent all the way down the chart, and this makes sense because it's actually just basically solving the same problem every single time. It's reduced the 5,000 row to the case of the 10 row. But the flip side of this is that as the representations get worse, when you increase the intrinsic dimension moving right on the plot, the performance gets slightly worse. So that's the trade-off there. But we can see, like in this low intrinsic dimension, high ambient dimension regime, most of the time it's just not possible to get a good estimate out of other estimators, and we kind of rescue this behavior with LMI. Okay, so this is nice, but it's like a really, really favorable setting, and also it's Gaussian data, and you might think, well, okay, if it's Gaussian data, we don't even need MI. If we want to capture dependence, we just use CCA or whatever, or like whatever linear method. So what about non-Gaussian data? So it's actually kind of non-trivial to benchmark MI estimators on complicated distributions, because analytically, most distributions are like not tractable to actually know the ground truth MI. So instead, we came up with a trick for creating artificially complicated distributions where we can get the ground truth MI. So I think the easiest way to demonstrate how this trick works is to just show you. So we start with some bivariate Bernoulli distributions. So we have like just a discrete binary here. And what we do is we drop in pictures to replace our binary labels. So instead of a 0, we replace it with a picture of a 0. And instead of a 1, we replace it with a picture of a 1. And we can show under like really, really weak assumptions that the MI between x and y in both cases should be identical. Okay? And here we do it with pictures of 0s and 1s because it's easy to understand, but we could, in principle, do this with like any data that has like really nice clustering properties. Okay, so we essentially use these types of data sets to benchmark. So here on the left scatter plot, the x-axis is like the ground truth MI of that simple distribution, and the y-axis is the estimate that we make from the complicated distribution. So in the existing estimators, you see two types of failure modes, basically. So for the classical like KSG non-parametric estimator, you see like really, really low variance. It looks quite nice. The only issue is that it systematically underestimates MI. And for the other two estimators, you see they get much closer to the ground truth, but they have this like crazy variance. And with LMI, we kind of reconcile both of these views. We have something with relatively low variance that's also relatively close to the true value. And one nice perk, which we didn't plan for, but it turned out that the runtime of LMI ends up being faster in our hands than the other three existing methods. Okay, so now we'll talk about like a real problem that we try to answer using our MI estimator. And specifically, we'll look at I guess self-fate commitment and hematopoiesis. So we'll work with this really, really nice data set from Alon Klein's lab from the paper that I showed the quote from, where it's single-cell RNA-seq profiles of differentiating mouse hematopoietic stem cells in a dish. So one really, really powerful thing about this data set is that it's lineage traced and sampled at multiple time points. So what happens is the cells get a clonal barcode, and then after 2 days, some of the cells are sequenced, and the remaining cells are split into 2 wells and allowed to differentiate until day 6, and they're sequenced again. So typically in single-cell RNA-seq, you can never track the dynamics of a cell because you have to kill the cell to get its transcriptome. So here in this lineage tracing setup, you do the next best thing, which is you sequence a cell, and then you also sequence its clone, and you know that they're clonally related, right? So what we can do is take cells from day 2 and match them to their twin cells from the day 6 conditions. And the reason that this like little like split well experiment is done is so that you can test essentially the presence of hidden variables in this system. So the idea is that if single-cell RNA-seq captures all of the variables relevant to cell fate, then once you split the cells at day 2, you shouldn't have any increasing information about fate commitment between the 2 wells, right? So the idea is if you know everything about cell fate at day 2, then looking at a day 2 cell should tell you just as much about fate as looking at a day 6 cell in a different well. Another way of saying this maybe more formally is this is a test of whether or not the dynamics are Markovian. And ideally, we would do this by estimating mutual information between the samples at day 2 and the day 6 well, and then between the 2 day 6 wells. Okay, so this is what they wanted to do in the original paper, but it turned out MI estimators don't work for this data, so they use some heuristic approaches to try to get at the same thing. But here what we can do is just take LMI and revisit the same problem and just make the estimates. So if we do that, what we find is that the mutual information between the day 2 and day 6 is 0.3, but then between the 2 day 6 wells is closer to 1. So we've seen that the information about cell fate increases between day 2 and day 6. So this says the dynamics are non-Markovian, and the likely reason for this is that there's some hidden information about cell fate that doesn't appear in the day 2 transcriptomes that does appear in day 6. And so this could be that there's like some chromatin state that's seen at day 2, or that exists at day 2 but is unseen by the single-cell RNA-seq, that emerges into a transcriptomic change by day 6. Okay? So with the MI estimate, one nice thing we can do is we can go further than just saying there's more cell fate information at day 6 versus day 2. We can try to pin down when exactly the cell fate information emerges. And the way we can do this is by decomposing our MI estimate into its pointwise contributions from each cell. So here what I'm showing is for all of the early time point cells, their contribution to the overall MI. So purple means low contribution. So at the top, you see essentially no contribution to the MI or mostly purple cells. And then as you start to go down the differentiation trajectories, you get more yellow. Okay? So we can try to look at this a bit more quantitatively. So you could pull out the neutrophil trajectory, which is like the orange one. And we can infer a pseudotime along this trajectory, which kind of just says how far down the path are you. And then we can compare this to the pointwise contributions at that point. And what we find is that they're kind of flat, and then at some point they just dramatically increase. And if we look at where that is on the UMAP, we see that it's right around this branch between monocyte and neutrophil. So it kind of intuitively makes sense that like once you go past that branch, you start to have like a dramatic increase in cell fate information. So this like intuitively makes sense. Okay, so here I showed one example of using LMI to study cell fate decisions from lineage trace single-cell RNA-seq data. But LMI is just a way of measuring statistical dependence, and it should work in principle for any high-dimensional data with low-dimensional structure. So in our paper, we looked at images, and we also looked at protein sequence embeddings from protein language models. And in some B-sides that didn't make the cut for the paper, we also looked at like estimating the mutual information between modalities of single-cell data, like the chromatin states in the RNA, or RNA in like a site-seq profile. And we also looked at chemical fingerprints, like in the context of small molecule drug screens. But there's really, probably many other interesting questions that you could ask with LMI, and I'd be super curious to hear people's thoughts on things that this could be useful for. And if you're interested in using LMI, I've tried to make it easy to use. So there's a documentation website, which is, I think, a bit sparse, but definitely workable example usage and API are there. And you can install it from pip, and then the estimate can be made essentially with one line of code. There are some like parameters that you can optimize if you want to, but every single estimate in our paper is made with this exact line of code, lmi.estimateXY. So you don't actually need to optimize too much if you don't want to, but you can always get like a tiny bit of better accuracy if you do. Okay, and if you run into any issues using LMI or any questions, feel free to reach out. And with that, I'll wrap up. I'd like to thank my co-authors, Peng, Alan, and Xiaokang, and the Wyss Institute for supporting me, and all of you for paying attention.
That's really interesting. I look forward to trying it out. I'm curious. I think I missed part of the sort of the concept when you were describing this idea that you could potentially have a correlated variable that gets lost in the reduction, and then you showed an example how you basically have some kind of optimization to make sure that doesn't happen. But presumably you have to do that iteratively over all of the different possible features. Like the optimization is like a min or a max over all the features. Is that how it works? To ensure that no individual feature gets lost, right?
Yeah, so what we do is we actually just predict the entire vector from the entire latent representation. So we don't consider features one at a time ever. We're just basically learning representations which are useful for predicting the other variable.
How is that different from an autoencoder?
So I would say it's an autoencoder with 2 extra pieces. It's like you take 2 autoencoders and then you add 2 extra decoders crossing across the...
I guess I'll just also build on that question. If I understood correctly, you're learning the latent representation at the same time that you're trying to not lose any information, and then you use the latent representation to compute the MIs. Do you have like a double dipping problem that then you have to compute the MI on the test samples?
Yeah, so so I guess a secret, not a secret thing, but a thing that's unwritten here is that there's actually 3 partitions of the data set. So we learn the representation on like 40% or 35%, or I forget what the default is, but we have like a test set within that half of the data. And then we use the other half, which has been never seen by the network.
Thanks. That was really interesting work. So for some applications, people are also interested in calculating stuff like conditional mutual information. So I wonder, like, have you thought about whether this framework could also be applied to like conditional mutual information estimation?
Yeah, I think that's a really interesting question and definitely something we've thought about. And I think in principle, it does fit into this. So there's like one very lazy way of doing it, which is to take these representations and then if you have like a separate z, if that's like a low dimensional z ideally, you can just throw that into the non-parametric KSG estimator, which estimates conditional mutual information. But then there's maybe a more clever way of doing this where you add like a third encoder to support like a high dimensional z, if that makes sense.
Hi, yeah, this is beautiful, and I really look forward to trying it out. Thank you for making software, too. So if I'm understanding right, it's sort of this two-step estimator to get the mutual information. And I mean, that runs into the, the data splitting problem at first. But the other assumption is that doing this cross-modality reconstruction maximizes the mutual information of the latent representation as well. And I'm wondering how you think that compares to something like, if you did have like a one-step estimator for just maximizing the representation, like, is that possible? Or
yeah.
Like,
so one step is definitely possible if you basically if you like instead of regularizing with cross prediction, if you regularize with like a differentiable mutual information estimator. That's something we explore. It's like buried in the appendix of our paper. But I think the fundamental reason why we don't do that is because those variational estimators tend to be very sample hungry. So if you're ever in the low sample regime, like 2,000 samples or under, you really want to be using the non-parametric estimator because it's just a lot more sample efficient in that regime. So that's the reason we have the two steps. But it's definitely possible to have a one step, and we do empirically compare and show that the two-step works better.
And then the cross-modality, like reconstruction, like it seems empirically this maximizes mutual information, but is there any like analytical?
Yeah.
Okay.
So we have so basically one way of thinking about prediction from X to Y is to think of it as minimizing the conditional entropy of X given Y. And this is a classical result in one dimension. Like you can open a textbook and find this. It's a bound, like upper bound from MSE to conditional entropy. And if we just like stack together this result a couple of times and then like add a few words in between, we get that maximizing the mutual information or minimizing the MSE is the same as maximizing the mutual or equivalent to maximizing minimizing an upper bound. For information. Yeah.
Okay, let's thank the speaker again.